Now let's talk about the activation energy. The activation energy is going to be the energy required to get a reaction started. But let's talk about a couple of examples of how reactions actually get started and as a function of temperature. For example, I used to live in Sacramento, and on a hot August day, it might be, one of the hottest days, 110 degrees Fahrenheit, which would be 40 couple degrees Celsius. But then I left my tuna sandwich in my car all afternoon. And on a hot in the car, it just takes all that energy in, and it can be, I don't know, it certainly feels like this, 160 degrees Fahrenheit. And I leave that tuna sandwich in there for, I get to school, get to campus in the morning, and leave it there for 5, 6, 7 hours. Should I eat it? What happens when you leave food in the hot temperatures? So bacteria grow, and they grow much faster as the temperature increases. And so the rate of reaction definitely depends on temperature. Now, I don't know, is it hot enough that it might actually kill the bacteria? I guess I'd have to talk to my food safety, ServSafe certified friends in order to figure that out for sure. But I would guess I would certainly not eat it. I would not take that chance. I've had food poisoning before. It is not fun. Now here's another example. It says the simplified burning of charcoal in a barbecue can be represented, charcoal can be represented by carbon. We can burn it. This is a combustion or burning reaction. We put it with oxygen, we get carbon dioxide. And if you've ever grilled on a barbecue or seen somebody, you know that the burning gives off energy. This is an exothermic reaction. And if we were to draw a reaction energy diagram, which we've done before, we would put potential energy on the y-axis, reaction progress on the x-axis, and because it's exothermic, we would draw our reactants having higher potential energy and our products having lower potential energy. And this difference in energy we call delta H reaction, the change in enthalpy of reaction, also called the change in heat energy of the reaction as it occurs. Okay, so this is a highly exothermic process. Heat is given off, and yet you can have a bag of charcoal that sits there for the longest period of time and does not react. Oops, I've got a little sunlight coming in here in the late afternoon. So, do you need to add energy to charcoal to get it to burn? The answer is yes. And that energy is called the activation energy. And that energy is called the activation energy. Now, once charcoal is burning, and so here's where we draw the activation energy. It is a little, or not little, but it is a energetic bump between reactants and products. And the activation energy, as we'll see, is defined from reactants to top of the hump. So this little place here, this energy is called the activation energy. And it is E sub A. Now, once charcoal is burning, do you need to keep adding more energy? And the answer is no. And the reason is that you get a lot of energy back, and that energy can then be used to as the activation energy for the rest of the charcoal, for the rest of what's going to burn. So once charcoal is burning, do you need? No, because the energy released then keeps the reaction going. So the energy released by the reaction keeps the reaction going. So, and that's why it just sits there for a very long time until you get it burning, until you put the lighter fluid or somehow start it burning, until you supply the activation energy. Now, let's do an activation energy for an endothermic reaction. And our endothermic reaction is going to be CO2. Well, we know that if we take an exothermic reaction and flip the reactants and products, the sign of delta H reaction changes. So we take the reaction that we just had. Now we know that it has to be endothermic. Energy is on the reactant side now, and our reaction energy diagram still has potential energy, still has reaction progress. But now we've got so these two have switched. Now we've got carbon dioxide as our reactant and carbon plus oxygen as our products. And the whole line is still the same. So everything about this graph is still the same, except how we define the activation energy. So the activation energy E sub A, is defined as the difference in energy between the reactants and the top of the hump. And we might call that an energy hump. So here, from reactants all the way to the top is the activation energy. And if we compare it to the activation energy in the other direction, so the activation energy will be much smaller. So the activation energy depends upon which way we're going. This top of the hump also has a name. So at the point where it is at the top, it's neither reactants nor products. It's called the transition state. And the transition state is identified as the highest energy species and higher than reactants and products. And the fact that it's higher means that it's, so the reactants and products are typically stable, meaning they don't react until you supply that activation energy. So if you're an endothermic reaction like this one here, not only do you have to have the energy of the delta H reaction for this process, but you also typically have to add more for the activation energy.